Good old thermodynamics. See, thermodynamics tells us why our coffee cools down and how ice melts on a hot day. But let's start more basic. Yeah, really basic. So let's start by defining some keywords. Energy is the capacity to do work or produce heat, while heat is the transfer of thermal energy between two objects with separate temperatures. And lastly, work is force acting over a distance. Now, these three words help build what we know as thermodynamics, which is a science and relationship between heat, work, temperature, and energy. Also good to know that state functions represent quantities or properties of a thermodynamic system, while non-state functions represent a process during which the state functions change. Now that we know our goal is to understand, let's delve into some other basic concepts. Potential energy is the energy stored in an object due to its position or configuration. And kinetic energy is the energy an object has due to its motion. For example, take a look at this ball. When it's at the top, it has more potential energy and less kinetic energy, but as it releases, it gets more kinetic energy and less potential energy. Have you ever played in the snow and you come home and sit in front of the fireplace? Well, you sit in front of the fireplace because of heat transfer, which is the process by which thermal energy moves from one object or substance to another due to a temperature difference. And since you are colder than the fireplace, as all heat does, it transfers until everything has the same temperature and equilibrium. Now, one thing you should get used to hearing are surroundings and systems. To explain this, think of any atom in a void. The system is the item where your attention is focused, and the surrounding is everything else in the universe. They combine to both make the whole universe. Now, in the major study of what heat and energy is, there has to be a way to describe how it acts in chemical reactions, as introducing endothermic and exothermic reactions. An endothermic reaction is when heat goes into a system, and since it's absorbing it from the surroundings, we might feel it as cold. While exothermic reactions are reactions where energy and heat are released and goes into the surroundings, and so if you were to feel them, the item would feel hot since you are literally touching heat and energy. Internal energy, abbreviated as E or delta E, is the sum of kinetic and potential energies of all particles in a system. Imagine any item. The number of particles in it would be massive and way too large to count. But this can be useful for counting the internal energy of a gas with the same type of molecules. The internal energy change can be simplified to delta E equals Q plus W, where Q is heat and W is work. See how useful those early vocab words are? If delta E is less than 0, energy is released and the reaction is exothermic. But if delta E is greater than 0, energy is absorbed and the reaction is endothermic. Joules are the units for both energy and work. And for most thermodynamic quantities, you can split them into two parts. The magnitude, which is the actual number, and the sign, which describes the flow of energy and helps describe whether heat is absorbed or released through it being positive or negative. Hopefully you're still following me as we get into one of the three major concepts in thermodynamics, enthalpy. Enthalpy is a state function defined as delta H, and it's usually measured in kilojoules, and represents the total heat content of a thermodynamic system. The difference between enthalpy and internal energy is that enthalpy is equal to heat absorbed or released at a constant pressure, while internal energy includes both heat and work. Now, to find enthalpy of a chemical reaction, all you have to do is subtract the enthalpy of the reactants and the enthalpy of the products. Now, we can find a way to use this in real-life experiments through calorimetry, which is a science of measuring heat, especially how much is absorbed or released. What you want to do is use a cup and essentially run a chemical reaction in it with a thermometer and measure the change in temperature. Now, the change in temperature can help us a lot with the amount of energy released or absorbed through a single equation. This equation is Q equals Cm delta T. Let's simplify, with Q being heat, C being specific heat capacity, which is the energy it takes to raise the temperature of 1 gram of substance by 1 degree Celsius. Essentially, each substance gets its own value and you just need to add it to the equation. M just means mass, and lastly, delta T is change in temperature in Celsius. If Q, or heat, is positive, it's absorbing heat, while if it's negative, it's releasing heat. Now, just based on that chemical reaction, we can find the change in temperature or heat just through some simple math. Now remember, heat is thermal energy stored in temperature-dependent motion of particles, including electrons, atomic nuclei, individual atoms, and molecules. One main concept here is that particles move faster at higher temperatures, and you can actually graph the movement of particles by frequency in an ideal gas, which follows all gas laws, and if you were to graph it, you would get the Maxwell-Boltzmann distribution. Just as some important general knowledge, force of attraction between particles is strong, which is why for some you need more energy as heat to break bonds to form new substances. you can find enthalpy of fusion as the energy needed to change a solid to a liquid, and energy of vaporization as the energy required to change a liquid to a gas. Now we cross the second main topic of thermodynamics, and probably the most important one, and that is entropy. See, entropy is defined as a measure of disorder, or also a measure of arrangements in microstates. To understand microstates is really just probability. Imagine that you have a gas of 4 atoms enclosed in a tank. If that tank is open, the gas can flow to another tank. If you find the probability of each order or microstates, you can find it's most probable that the gas ends up split with 2 atoms in each tank, since it has the most microstates. So understanding that entropy means having more microstates, what would you say has more entropy, ice or water? Well, the answer is water. See, we can write an inequality. The S, or defined as entropy, of a solid is less than the S of a liquid, which is less than the S of a gas. An easy way to understand this is if the item is more concentrated, it'll have less microstates possible, which leads to less entropy. But if a substance, let's say a gas, which has so much space and is more spread out, has more microstates, it has way more entropy. If entropy, or delta S, is negative, then the reaction is endothermic, but if delta S is positive, then the reaction is exothermic. Now that we understand how entropy works and how enthalpy works, we can take it to Gibbs free energy. See, Gibbs free energy is just another thermodynamic value, which pretty much just combines information we know about the entropy of a substance and the information about the enthalpy of a substance into one easy value for us to understand, as delta G, or Gibbs free energy, is equal to delta H, or enthalpy, minus T, which is temperature, delta S, which is entropy. If delta G is positive, then the reaction is endothermic, non-spontaneous, and decreases in entropy, while if delta G is negative, the reaction is exothermic, spontaneous, and increases entropy. We're pretty much done here. Now that we've understood all the major concepts, we can apply them to the 4 main laws of thermodynamics. Since everything has to be in 3 laws, when there was a 4th edition, it just went as the Zeroth Law. And it states, if 2 systems are in each thermal equilibrium with the 3rd system, then they are in thermal equilibrium with each other. Thermal equilibrium is just having no heat transfer between both systems because they're both the same temperature. So, if A has the same temperature as B, and B has the same temperature as C, then you can say A and C also have the same temperature. The first law of thermodynamics, or also known as the law of conservation of energy, states that energy can be converted from one form to another, but cannot be created or destroyed, and that the total energy in the universe is constant. The second law of thermodynamics states that the entropy of the entire universe as an isolated system will increase over time. The second law also states that the changes in entropy in the universe can never be negative. Last but not least, the third law of thermodynamics states that the entropy of a perfect crystal at 0 degrees Kelvin is 0, and that the entropy increases with temperature. A great way to understand entropy increasing with temperature is remembering that entropy of a gas is more than an entropy of a liquid, which has more entropy than a solid. Now hopefully you've understood everything there is to know about thermodynamics in a time-worldly manner. If you enjoyed the video, don't forget to hit the like button and the subscribe button. If you have any suggestions for future videos, make sure to put them in the comments. And without any further ado, that is all. Have a great rest of your day.